We are live. Good afternoon, everybody. I'm Jean-Claude Zambrini, and it is a special pleasure for me to chair the session of Martin Eyrer. I first met him in 2003 when he was invited speaker at the International Congress on Mathematical Physics, organized in Lisbon by GFM. Since then, to say the least, his career has been spectacular. Martin started a collection of international prizes in 2008. I have counted 7 of them until today. Today, June 13, 2021. Beside the Field Prize in 2014, I would stress the Breakthrough Prize in Mathematics that he got this year. This one is founded by Mark Zuckerberg and Yuri Milner. The first sponsor doesn't need an introduction, but the second, interestingly, conducted research in quantum field theory before to become a millionaire, high-tech investor and philanthropist. So you will not be surprised that this Breakthrough Prize is more generous money-wise than the field one. In the future, maybe science will be more often sponsored by billionaires than by state agencies or IMU. I give the floor to Martin.
Thank you very much. And well, I'd like to thank the organizers for the invitation. It's a pleasure to be here, well, virtually be in Portugal again. So the talk today is based on joint work. So I don't know, can you see my other slides live?
I have the title only.
Okay, I think they're fine now. Yes, good. So today I'm going to talk about, well, some steps that we did towards constructing Euclidean Young-Mills theory. And this is all joint work with A.J. Chandra, who's also at Imperial College London, Ilya Sheverev, who is now in Edinburgh, and Hao Shen, who is at University of Wisconsin-Madison. And it doesn't matter if you never heard the words in the title, I'm going to try to explain that. And so to start with, when we talk about Euclidean quantum field theory, basically the setting is the following. So you start from some functional on a space of fields. And the sort of thing that you should have in mind is, for example, S of phi to be something like integral of gradient phi square dx, so like the H1 norm, square of the H1 norm. So that's the typical, that's the easiest kind of functional that you should have in mind. So it's something along these lines. And then given such a functional, Euclidean quantum field theory essentially boils down to trying to make sense of a probability measure on a space of fields, which formally would be given by e to the minus your action functional. Okay, so you have your action functional S, and you try to make sense of the measure e to the minus S, and this d phi here, you should think of it as being Lebesgue measure. And of course, as you probably all know, Lebesgue measure doesn't exist on infinite dimensional spaces. And so you cannot just interpret this naively, if you want, as a rather Nicodean derivative with respect to some reference measure. Okay, so you have to do something else. If S is quadratic, like in the example I gave you, well, then a measure which is of the form e to the minus quadratic form times Lebesgue measure, that would be a Gaussian measure. And so then, of course, we know how to relate the quadratic form to the covariance of the Gaussian measure. Basically, you just take the inverse of the operator that appears in the bilinear form. So in this case, it would be the Green's function of the Laplacian. And so in this particular example, the measure, which is called the free field, would just be the Gaussian measure that has as its correlation function the Green's function of the Laplacian. Okay? But in general, you can't do that. So the interesting functionals are not going to be quadratic. It's precisely the non-quadratic part that correspond to interactions in your field theory. And the hope then would be try to find some kind of approximation procedure. So for example, approximate your space of fields by some kind of finite dimensional space, maybe by discretization or something like that. Try to find sort of a natural corresponding discretization of your action functional, and then try to take some kind of weak limit. Right? So the hope then is if S kind of grows enough in all directions in some sense, then there might be hope that such a weak limit exists for some class of approximation. And if you're lucky, maybe it doesn't depend too much on the approximation that you choose. Now, of course, a similar kind of setup also shows up in statistical mechanics. Right? So there's a very close link between Euclidean quantum field theories and statistical mechanics. And in statistical mechanics, if you want, S would be the Hamiltonian or the energy functional of your system. And then a measure of this type would be called the Gibbs measure, the canonical measure, if you want, for your statistical mechanics model. But today, in this talk, I want to focus on one specific example of action functional, and that's the action functional that corresponds to Young-Mills theory. So Young-Mills is, if you want, the most commonly studied example of a gauge theory. I'm going to explain in a second, how to define these Young-Mills theories, or if you want, what the action functional is in the case of the Young-Mills theory. And this is really motivated by quantum field theory and not so much by statistical mechanics. Now, the setting is the following. So you start with a compact Lie group, G, which is usually called the structure group. And the sort of thing that you should have in mind is just, SON, for example, or SUN, or something like that. And then the space of fields is going to be, at least it's canonically identified, with the space of one forms on your underlying space. And the underlying space, it's actually the underlying space time, which we're always going to take the torus, the d-dimensional torus. And so a field is a one form on your space-time, so on the torus, which takes values in G. Right? So G is the Lie algebra that corresponds to this Lie group. And you should really think of this not so much as a one form, but actually as a connection on the trivial bundle. And let me try to explain by a picture what we sort of mean. So if you take, say, G equal to U1, so then it would just be a circle. And I take D equal 1. So I just take S1 here also, or even R. So then TD times G is just some kind of cylinder like this. And the picture you should have in mind is that on each fiber of this cylinder, you don't have a canonical choice of origin, right? So you have this, if you want, it's TD times G. So of course, the way I wrote it down, there is a canonical choice of origin because G has a canonical, there's the identity element of G, which gives you a choice of origin. But that's just because here we focus, if you want, on the simplest possible example. And so what you should really have in mind is that there isn't a canonical choice of origin for each of the copies of G, right? So this is really a principal bundle rather than a product space. And so now a connection gives you a way of somehow lifting curves from the base space to the bundle, right? So if I fix a connection here, in this particular example, the base space is just a line, and then lifting the line to this bundle just means, you sort of choose basically a line like that. And now if I want to describe a different choice of horizontal lift, but starting from the same point, then what do I have to do? Well, at every point, you see, when I am on one of these fibers, so say I've already built a piece of my horizontal lift up to here, for example, and then what I have to tell you is in which direction do you move, right? In which direction do you want to move further? So I have to sort of give you a tangent vector here, which tells you in which direction you're going to move from this point. But then again, since there's no canonical coordinate system, the only way I can do that is if I have some kind of reference. And the reference that I have is that at that fiber, I already have my reference connection. So that one gives me a direction. And since I have an action of the group G on this whole, on this space, I can move, right? I can move that vector in this direction. So that gives me now a reference direction, which is given by the original connection. And so now if I give you, I can, if you want, describe the direction of the pink vector in terms of the, with respect to the yellow one. And then that would be given by an element, since we're in the tangent space, so that would be described by an element of G, right, of the Lie algebra. And so in this way, you can see that if I'm given a reference connection on that bundle, which I can fix once and for all, if you should think of that as like fixing a coordinate system, then that gives me a way of making horizontal lifts with respect to the reference connection. And if I want to describe any other connection, I can actually describe it by a G-valued one form. And that just tells me by how much at every point, the direction in which my horizontal lift points differs from the one that's given by the reference connection. Okay, so in this way, so in these gauge theories, the natural notion of a field is a connection or an equivariant connection, but we're always going to describe such a connection by simply a one form with values in the Lie algebra. Okay, so that's the space of fields. And then what's the action functional in the case of Young-Mills? Well, the action, once you have such a connection, so I write it in coordinates here, so a connection here is really just given by collection of AIs with I going from 1 to D, right? That's how you would describe a one form in coordinates. And each of the AIs now is just a function from the torus into the Lie algebra G. And given such a connection, there is a notion of curvature associated to it. And the curvature is a two form. So it's this Fij, which is given by this formula here, where the first term is just the exterior derivative of the one form A. So that gives you a two form. And then there's an additional term, which is, so here the brackets are just the Lie brackets in G. So remember, AI and AJ are functions with values in G. And so then I take the Lie bracket between the two. And you add this, that gives you the curvature of your one form. And you see that this is antisymmetric. So this is an antisymmetric. So it is a two form. Well, this term is obviously antisymmetric, and this term is antisymmetric because of the antisymmetry of the Lie bracket. Right. Jean-Claude, are you saying something? Or I don't hear you, but I see your lips moving.
No,
okay, sorry.
I'm saying anything. Sorry.
And then the Young-Mills action is just the L2 norm of the curvature. Okay, and you see it has some similarity with the simple example that I gave you at the very beginning, where the action was just the H1 norm of the field. And well, because it's, the L2 norm of the curvature, and the curvature is basically a derivative of the field plus just some additional correction term, if you want. Now, what makes it special, and this is, if you want, the special feature of gauge theories, is that there is an action, there is a natural action on the space of connections, which is given by what's called the gauge group. So the gauge group is just smooth functions with values in G. So functions on the underlying space-time, which is your TD, with values in the Lie group G. Now this is a group, right, simply under pointwise multiplication. And that group acts onto your connection essentially by changes of coordinates, right? So you remember in my picture earlier, I said in this simple example, I mentioned that you should think of each fiber not really having a distinguished origin, and the action of this gauge group corresponds to changing the origin on each one of the fibers, right? So you give yourself a function from the torus into G, and now that would just pointwise, it sort of acts on that copy of G at every point of the torus, and that just corresponds to some kind of change of origin in these fibers. And then, if you take the interpretation of A as a connection, via the way it generates horizontal lifts, as I described it earlier, you can kind of figure out how that transforms under these changes of coordinates. Okay, and the way it transforms is like this. So basically, you have a pointwise conjugation with G. Or if you want, I could have written this. Yes, I could have written as add G of A if you want. And then there's this additional term, which is the differential, essentially the derivative of G. Right? So this, again, you see that this is naturally one form, is the differential of G, the derivative of G at one point belongs to the tangent space of, the Lie group at the point where you are, and then the G inverse moves that tangent space back to the tangent space at the origin, which then gives you an element of the Lie algebra. Okay, so this is an element of the Lie algebra, and this is also an element of the Lie algebra. And so you have this invariance of the, so you have this action of the gauge group on your space of connections. And it turns out that this curvature tensor is intrinsic, so in the sense that it's independent, coordinate independent with this notion of changes of coordinates. Right? So in the sense that if I replace A by AG, according to this formula, and I compute the curvature for AG, then what we find is that you get the same, or maybe it just gets conjugation with G. So, but then by the time you take the L2 norm, you get the same. Yeah? And so this action here is invariant under the action of this gauge group. So now what this tells you is that it's not very coercive, right? So in the previous example, the action was just the H1 norm of your field, and that you can kind of think of it as being, it's like a non-degenerate quadratic functional that really grows pretty fast in all directions. So here you have many directions in which this action functional is actually constant, right? So there are, and this is an infinite dimensional group. So there are infinitely many directions at every point in which this action functional doesn't change. And now that's obviously a problem, right? So, because remember, what we want to do is we want to build the measure, which is at least formally given by e to the minus this action functional. But now if the action functional is kind of flat, in infinitely many directions, then there are kind of there's sort of infinite dimensional subspaces in the direction of which your measure should look like Lebesgue measure, right? And as I already mentioned at the very beginning, there is no Lebesgue measure in infinite dimensions, and so you wouldn't expect such a measure to exist. Right? And so then, of course, you might think, well, that's the end of the story. Obviously, it's not the end of the story, and the reason why it's not the end of the story is because in your gauge theory, the physical observables are those functions of your space of fields that are themselves invariant under the action of the gauge group. Okay, and so here all physical observables, so a physical observable would just be a function of your state space. Your state space here is now the space of connections. So let me write O for a physical observable. And physical observables are gauge invariant in the sense that, O of A acted upon by one of these coordinate transformation is the same, independently of which transformation you choose. Okay? So that tells you that, well, on the one hand, your measure is supposed to kind of look like Lebesgue measure in these infinitely many directions, but then these directions, we really don't care about them, because as soon as we look at things that are physically meaningful, they don't actually see these directions, right? You can move in these directions as much as you want, your observable doesn't change. And so morally, what this tells you is that if you modify your measure in some sense only in those directions, well, then that doesn't actually change anything as far as physical observables are concerned, right? And that can give you a hope that it is actually possible maybe to define this measure. So an example of such a physical observable, and that's the canonical example, as if you want the best known example of such a physical observable, is what's called the Wilson loop. And so here what you do is you take a loop. So a loop is a function, from 0, 1 into your torus, but so that the value at 0 and the value at 1 are the same. And you take a class function on your group, so a function which only depends on conjugacy classes, which is the same on every conjugacy class. And then given such a loop and a class function, you have an observable which is given by, well, take that loop, lift it look at the horizontal lift onto your bundle, right? So the loop is in TD. So I mentioned earlier that the connections gives you a way of making a horizontal lift of that on to TD times G. And then for the horizontal lift, well, you can start anywhere at 0. You look at where you arrive on the same fiber, where you are at time 1, and then you're going to be somewhere else. You multiply the two values, or the inverse of one with the other one. So then the effect of that is that what you get doesn't actually depend on where you start on the fiber. And then you apply the class function to this. And it's not too difficult somehow to check that what you get in this way is actually independent of the action of the gauge group. Right? So if you act with the gauge group on A, so if you replace A by AG for some G, and you perform exactly the same procedure, you're going to get the same answer. And so that's a large class of physical observables. Actually, this class is really exhaustive in the sense that if you know all of these observables, then you know, if you want, which orbit of the gauge group you belong to. And so the conclusion here is that instead of building the measure mu on the space of connections, which is problematic because of these infinitely many flat directions, we really just need to build it sort of on the quotient space of connections quotiented by the action of the gauge group, right? So we basically postulate here that A is equivalent to AG for every G in the gauge group. Okay? And then we just quotient by this equivalence relation. And now what we really want to do is to actually build a measure on that quotient space. Now, still, it's not obvious how that works now, because so one problem of this quotient space is that that space is really not linear anymore, right? So the space of connections was basically a linear space because it was these Lie algebra valued one forms, so that's a nice linear space. So there is at least a notion of like reference Gaussian measures and so on this space. By the time you quotient it by the action of the gauge group, you get a nonlinear space, and you start to also run into all sorts of topological problems, which is that, you know, if you want to do analysis on these, then you really need to put a topology. So you could take the space of smooth connections and quotient by the space of smooth functions with values in G, and that gives you a nice quotient space, which is actually kind of locally looks like a space of functions. But then the measure that you're trying to build, you know, in some sense, whichever way you're going to try to approximate it, it's not going to live on a space of smooth functions, right? So you have to allow for much more singular kind of connections if you want to build a proper probability measure. And, you know, and then you have to actually start to think about what's a good topology to choose here. And, you know, whether this quotienting operation actually is compatible, if you want, with the topology that you choose. And you still have to somehow approximate that measure, and you have to, you know, show that the approximations converge. Now, before I continue, so let me give you a bit of an overview of some previous results in this direction. And there's a huge difference between the two-dimensional case and the higher dimensional case. The most interesting case, of course, in principle, is the four-dimensional case, since the base space is supposed to be space-time, and now space-time is four-dimensional. But four is somehow the critical dimension in some sense for this Young-Mills energy. And that's very difficult. It's very, very difficult to basically do anything in 4 dimensions. So we're not going to talk much about 4 dimensions today. In 2 dimensions, a lot is known. And so that started sort of in the very late 70s, early 80s by a construction of Bridges, Fröhlich, and Seiler. So they looked at the abelian case, so where, you know, the structure group G is actually abelian. So that, of course, you know, lots of the difficulties drop. So in this particular case, if I only care about the Young-Mills measure, then it becomes kind of trivial, because if it's abelian, then this is 0. And then F is linear in A. And so S is quadratic in A. And then I'm actually back in the case where the measure is just Gaussian. And so in this case, just looking at the pure Young-Mills measure is not very interesting, because it's just a Gaussian measure, which you can describe very explicitly. And so the interesting case there is to build the Young-Mills measure that interacts with the Higgs field. So there's an additional field that interacts with this Young-Mills field. And that's what Bridges, Fröhlich, and Seiler did in the late 70s. And then in the and then there was some later work also by Grosking and Sengupta, still in the free case, in the abelian case. So in the non-abelian case, in the early 90s, Sengupta basically came up with a pretty much explicit guess for the joint distribution of the Wilson loop observables under the Young-Mills measure, even in the non-abelian case. And so that was essentially came as a guess by looking at what happens in a discrete case. So you take some kind of space discretization, so you build a lattice gauge theory model, And then you look at what the Wilson loop observables look like in the lattice gauge theory, and then you try to guess what the limit is as you go pass to the continuum limit. And you can actually do that in 2 dimensions. And that was later picked up by Thierry Lévy, also in the early 2000s, who made sort of certain number of things more precise. And also very recently, Ilya Sheverev, for example, managed to also build a state space for a space of connection, build an actual probability measure on a space of connections, which is such that the joint distribution of the Wilson loop observables coincides with the distribution that was guessed by Sengupta. So the 2-dimensional case now is very well understood, mainly thanks to the fact that you have this almost explicit kind of expression for the joint distribution of the Wilson loop observables. But that's not the case in 3 dimensions, so you don't have any guess like that. And so much, much less is known in 3 dimensions. And also in 3 dimensions, the field lives on much more singular kind of connections or distributional connections, right? So in this business, the higher the dimension, the more singular these measures become, or the more singular the fields on which these measures live become. And 2-dimension is somehow the borderline, where the field, it's not quite a function anymore. It is actually a distribution, but it's a distribution that is very close to being a function. And this goes worse in higher dimensions. And in 3 dimensions, so there's a series, well, there are several series of works, one by Balaban, one by Federbush, and then there's also a separate work by Magnan, Vivasor, and Seneo. And that's, I think, one of the few works in 4 that says something about the 4-dimensional case. And in these works, they take an approach which is somewhat similar to that by Feldman, Glim, and Jaffe when they constructed the 5-4 theory in 3-dimension back in the late 70s. They obtain some type of effective theory, but it seems very difficult to extract from these work, any sort of interpretation in the way that I just gave it, right? So, I mean, what you would really want is an actual state space, a probability measure on that state space, and then a class of observables which are sort of measurable or continuous functions on that state space. And it's actually very difficult to extract something like that from these works, because they're really formulated in a somewhat different way. Now, very recently, there's a work by Kao and Chatterjee, which is not yet available. I think there's a YouTube talk by Chatterjee, which is available, where they build a candidate state space for the 3-dimensional and possibly also the 4-dimensional case. And what we're going to see is that, well, so we also built some candidate state space. The link to the work by Kao and Chatterjee is that, so our space can be interpreted as a subset of theirs, endowed with a quite a bit stronger topology. And then maybe I should also mention, so there are various results where in the special case where G is ON or UN or SON, so there are various versions, with n going to infinity. So then again, if you let n go to infinity, then you can again guess certain things. So that's one limit that has been studied a lot, but that's really a sort of a generalization which is somewhat orthogonal to what I want to talk about today. So the approach that we wanted to follow is so what usually goes under the name of stochastic quantization, and that was proposed by Parisi and Wu in the sort of mid to late 80s. And the starting point, sort of the idea there, is the following. It says if you have a measure which is of the form, e to the minus an action functional times Lebesgue measure, and so now think again of phi as being some finite dimensional discrete approximation of your field. So think of phi as being an element of Rn for some very large n. Then you can actually show, so that's a sort of easy exercise in stochastic calculus, that if you look at this stochastic differential equation, which is basically just a gradient flow, it's just a gradient descent for the action functional, but then plus white noise. And so this white noise is somehow the white noise that has like independent components in all directions. Or if you want, here, if you take a gradient, if you take a more fancy kind of gradient, if there's more structure in your space and you take a natural gradient that maybe goes with the additional structure of your space, then this noise here should be the noise that has the covariant given by basically the inverse metric tensor of the metrics that you used in order to define your gradient. Right? So if you look at this differential equation, stochastic differential equation, then you can check that this measure is invariant in the sense that if you start with an initial condition which is random, independent of the driving noise here, and which is distributed according to this measure, and then you run it for any fixed time t, and you look at the law of the solution, then the law is also given by the same measure. And so in particular, what you expect is that if you start with sort of pretty much any initial condition, and you look at the solutions to this equation, if you look at what happens after a very long time, you would expect this to converge to something stationary, and then the only stationary measure is this measure here. Right? So what you would expect then is that after a long time, whatever the initial condition, you can just start at 0, for example, then after a long time, the law of the solution should converge to this probability measure. Okay, that's what you hope. And so then, you can take this on its back. So if you're able to give a meaning to this dynamic, then you can somehow define this measure as being the measure which is invariant for this dynamic. Right? So that would be one way of going about it. And so the hope here is now that instead of looking at some smoothened out or discrete or something approximation to your measure, you look at some kind of smoothened out or discrete or something approximation to this dynamic, and you try to pass to the limit there. And hopefully that's easier. You can somehow exploit the dynamical aspects to pass to the limit. And so that was the hope of Parisi and Wu back in the 80s. So if we do that, so in the case of Young-Mills, of course, the space of fields here is our space of connections with values in the Lie algebra. And so this evolution equation would actually be a stochastic partial differential equation. This will be an evolution in a space of one forms. So if you just do the calculation, if you compute the functional gradient of that Young-Mills functional, what you find is that it's given by some term like this, which it doesn't really matter. So this is, again, some kind of a deformed version of the exterior derivative and of the adjoint of the exterior derivative. And this guy is the associated noise, and this noise is just white noise, both in space and in time. So this guy is white noise in space-time. The exact form of the equation in local coordinates doesn't really matter too much. What's important here is that if you look at it, it's of this form. So there's a heat equation part, but then unfortunately there's this additional second order term which destroys the ellipticity of this equation, or the parabolicity of the evolution equation. And then there are some lower order terms. What I mean by lower order terms is it's terms that are local in A and the first derivative of A, but they don't involve the second derivatives of A. Okay, so they only involve A itself and the first derivative of A. Actually, there's one term which is cubic in A, and there's one term which is bilinear in A and its derivative. So the fact that it's not parabolic is a problem, right? And the reason is that's very strongly related to the fact that, you know, we have these infinitely many directions in which the Young-Mills functional is flat, right? And so in these directions, you don't expect to have any kind of mechanism that, you know, is coercive or sort of brings you back towards the origin or into compact regions of your space of connections, right? And so you wouldn't expect to get a parabolic equation, right? Because a parabolic equation you can start with any sort of field, you end up in some kind of compact region of your space of fields, and that's not what you would expect for the Young-Mills energy functional. But now, and this is problematic when you want to analyze this equation. And the trick, which was originally introduced by de Turck in the context of the Ricci flow, which has a similar kind of problem, and then was applied by Donaldson to the study of the Young-Mills flow, is to say, well, you know, since at the end of the day, we only care about physical observables, and, you know, so as I mentioned early on, we can modify things, if you want, in the unphysical directions without actually changing anything as far as physical observables are concerned. So we can, if you think, you know, you have these gauge orbits, right? So here, each gauge orbit, right? So if you have a connection A, here you would have the AGs. So that's the set of all the AGs, if you want. It's a cartoon of the AGs for a given A. And you have your Young-Mills flow, which, you know, sort of points, you know, in some direction here. So if you want, this here is the vector field in your space of connections, which is given by the right-hand side of this equation, right? So it's sort of the gradient of your Young-Mills functional. And so the idea now is to say, well, if I add to this anything that kind of points along the orbit, then that doesn't change anything as far as physical observables are concerned, right? So if I add to this vector field any vector field that is transverse, that kind of points in the direction of the orbits, then, well, that just pushes my solutions along the gauge orbits. But since all the physical observables are constant on the gauge orbits, it doesn't change anything as far as physical observables are concerned, right? So we can add anything to the right-hand side of this equation, which at every point sort of points in the directions of the gauge orbit. And in particular, so there's one trick, which is to make this particular choice, which, you know, creates additional messy terms of lower order, but gets rid of this term here. Right? So after you do this, you end up with actually a nice parabolic equation, driven by the space-time white noise. And then the question is, you know, is there a good interpretation of this equation? Can you build a nice state space? And do you actually, is your interpretation coherent in the sense that what you would want is to get in the end, you would want to build a Markov process on the space of gauge orbits. And so one property that you would want is that if you take two initial conditions, right, so say one here, that lie on the same gauge orbit, and now you look at the two solutions. So you have one solution here, so now that's a stochastic process, and you look at the stochastic process corresponding to this initial condition, then you would want to say, you would want to be able to obtain this stochastic process here as a gauge transformation of this one, right? possibly random, possibly time dependent, but it should be, but you would want to have a, by the time you take the quotient, you would want to still get a Markov process, right? And that would mean that if you take two different initial conditions, you can go from one to the other one by a gauge transformation, right? Possibly random. Okay. Now, one problem, so of course there's the general problem with these type of equations. So the general form of our equation now is the following, right? So there's a heat equation part, there's a bilinear term in A and its derivative, and there's a trilinear term in A, and then there is this white noise term. You can guess how regular solutions would be by just ignoring these terms and looking at the linear equation. And the regularity that you get is basically regularity of order, Hölder of order alpha, but for alpha less than -1/2. So it's some kind of negative Hölder regularity. So you get distribution valued solutions. And that's actually problematic for even interpreting the equation, because these are sort of it just involves pointwise products, and you can't take pointwise products of things like that. So then, the natural procedure that you would want to do is sort of smoothen that out, and somehow look at the smoothened equation passed to the limit. And the problem is that, right, so this equation is very rigid. So you're not allowed to, right? So if you add additional terms to this equation, well, then it's not going to be gauge invariant anymore, for starters. And so heuristic suggests that if you actually simply smoothen out the noise and try to pass to the limit, it's not going to converge. On the other hand, well, what you should do is add some counter term. And in this particular case, it turns out that the counter term is just linear in A. And then from somehow a whole series of general results that are obtained with various co-authors, you can just from general principles, this falls into the category of equations that we can deal with. And you have theorems that tell you that there is a limit if you choose these constants in the right way. But the problem now is that you've modified the equation in a way that appears to break gauge invariance or gauge equivariance of these equations. Except that actually what happens is that you break it in two ways, because smoothing out the noise is also an operation which is not gauge invariant. Right? So you actually break gauge invariance here in two ways. On the one hand, by smoothing out the noise. On the other hand, by adding this extra linear term. And so then there is a hope still that somehow these two ways of breaking gauge invariance somehow cancel each other out, and that in the limit it's actually restored. And so that's the result that we can prove. So let me now sort of state, if you want, informally, the result that we have in 2 dimensions. So in 2 dimensions, we can find a state space. So we can find a space of distributional one forms, and a space of gauge transformation. So here it is actually really just the space of Hölder continuous, right? It's just the functions from the torus into G that are Hölder continuous of order alpha. And furthermore, you can show that if you choose these constants C epsilon in the right way, there exists a choice so that, well, these approximate solutions converge to some limit in that space, modulo possible blow up. This space is kind of a nice space in the sense that like smooth connections are dense in it. So it really is, you can really interpret it as a space of connections. You can take the quotient, and the quotient is a nice Polish space. So it has a metric, it's complete separable and so on. That's not obvious at all, right? So in general, if you have a space and you have a group action on it, the quotient has absolutely no reason to inherit any sort of topological properties from the space that you start from, right? So here it turns out that the quotient space is actually very nice. it's the type of space that you can do probability theory on. And the Wilson loop observables are well defined on that space, and they're continuous. And there exists a unique choice of these constants, so that the miracle that I alluded to early on happens. Okay, so that there is this kind of cancellation between the way in which you're breaking gauge invariance by smoothing the noise and the way that you're breaking it by adding this linear term. And it just cancels out. There's a unique choice of these constants, which makes it cancel out in just the right way, so that the limit has that property that by the time you pass to the quotient, you still have the Markov property. Right? So that, like, for two equivalent initial conditions, the solutions are related to each other by a random gauge transformation. So of course, and furthermore, you can even prove that the process had at most one invariant measure on that space. And so, of course, the conjecture, so that's not a theorem yet, the conjecture is that it actually has exactly one invariant measure, and that measure should, coincide with the measure constructed by Gupta, Levy, and company. Right? I mean, in the sense that, you have a measure on that quotient space, and Wilson loop observables are just continuous functions on that space. And so you can look at joint laws of them under that measure, and these joint laws should coincide with the ones that were computed by Gupta. And in 3 dimensions, there's sort of there's a number of problems that you have when you try to extend the proof to 3 dimensions, which come from the fact that the solutions become much more singular. And in particular, the Wilson loop observables are not actually expected to exist. So they're already problematic even in the abelian case. They kind of blow up. And the reason is that the free field in 3 dimensions cannot be restricted to smooth lines, whereas in 2 dimensions it can. And the reason is basically that the Green's function of the Laplacian in 3 dimensions is 1 over x, and 1 over x is not locally integrable in 1 dimension. Right? If you restrict it to a 1-dimensional line, 1 over x is not integrable. Whereas in 2 dimensions, the Green's function is a log, and the log is integrable in 1 dimension. And so this is kind of problematic. And actually, even the deterministic Young-Mills heat flow, if you ask yourself what is the smallest beta, so that if you start with a distribution in C beta, that the deterministic Young-Mills heat flow is sort of continuous, say, for initial conditions in C beta, then you find that -1/2 is actually just a borderline. So this should be minus here. So there's a minus missing here. But the solutions do not belong to C -1/2, right? So you're even below the borderline for which even the solutions to the deterministic flow exist. So we can still do something. So we have some partial results in 3 dimensions. And the point is here that we can find a space of distribution of valued 1 form with, this time it's not a linear space. Okay, it's a metric space, but it's not a linear space of distributions. It's a subset of some distributional space, which is a linear space. And this space is such that on the one hand, the limiting solutions do live, so they do exist, so you can still find limits. They do belong to that space. And on that space, the deterministic Young-Mills heat flow is actually well posed. And so there is a gauge invariant way of smoothing connections in that space. And then that gives you a natural notion of gauge equivalence, and then it also gives you a natural notion of smoothened out Wilson loop observables. So you have at least something that's still left over. And we can say a little bit something about the quotient space. It's not as nice as in the 2-dimensional case, but it's still sort of just nice enough to do probability on. But I think I'm running out of time, so I should probably stop here. So I leave a few open questions here on the slide, and I thank you for your attention.
Thank you, Martin, for this beautiful talk. I have one question coming from Zemouran, who is a mathematical physicist of the Institut Supérieur Technico. I think the answer is contained in your first theorem, but I still give you the question. He was wondering why we should expect that Wilson variable should be good random variable, and he believed that you should spare those random variable, but then you will lose the Gaussian invariance. So it is this compensation phenomena you allude to.
Right. So yeah, so as you say, so in 2 dimensions, we can build a state space for which the Wilson loop observables are actually continuous, and so there is no problem. And in 3 dimensions, you need to smear them, but you smear them by the Young-Mills heat flow, which is gauge invariant. Right? So then you can smear them in a gauge invariant way. And here the point of the 3-dimensional result is that we can find a space which is on the one hand big enough to contain the limits of these approximate solutions, and on the other hand small enough so that the Young-Mill heat flow is actually well defined on that space, right? So there's sort of 2 competing things, and in 3 dimension, I mean, that competition is sort of very much on the borderline, but it just works out.
Thank you. I don't know if we're still a couple of minutes or not. I don't see any alarms running, so
I think we have 1 minute.
1 minute. So in 1 minute, there are much more physicists in the audience than usually. So where the idea that they know, they don't know stochastic analysis, but in the tool that they have, where renormalization come in somehow. You mentioned these, the word appear in your talk. So in 1 minute, can you say about it?
Yeah, so I think, I mean, one thing which is interesting here, right, is that the renormalization that we choose breaks the gauge invariance. So very often when in the physics literature, what people try to do sometimes is you try to find ways of regularizing this equation which preserves gauge invariance, right? And this doesn't, right? So this does not preserve gauge invariance. Now, of course, if you preserve gauge invariance all the way through the regularization, well, then, you know, it would be much easier to show that it's preserved in the limit, but it seems very hard to come up with something which is mathematically meaningful, which regularizes this equation and preserves gauge invariance. And so we use kind of symmetry arguments to show, right? So here, it's kind of subtle that in the limit, gauge invariance is recovered. And of course, this sort of forces you to choose these counterterms, to choose the renormalization constant in that counterterm in a very precise way, because if you choose it wrong, then you would definitely break the gauge invariance because you would add a mass term to your equation and that breaks it. So in 2 dimensions, you can show that somewhat explicitly. I mean, you can kind of just compute, if you want, the counterterm that is in some sense generated by this modification and the counterterm and this counterterm here. You can kind of show, you can show by hand that there is this cancellation. Okay, so maybe I shouldn't go more into detail because we don't really have time, but in 2 dimensions, you can basically show it by hand. In 3 dimensions, it's hopeless to show it by hand because you have logarithmic divergences and there's like many of them. So it's not like in 543 where there's one logarithmic subdivergence that you can compute. Here there's like 100 of them or so, and they need to cancel out in just the right way. And so it's completely hopeless to do it by explicit calculations. So you actually have to come up with some kind of symmetry arguments. And that actually works. So you can come up with some kind of symmetry argument to show that, right, that in the limit, that it must be possible to actually renormalize it in such a way that the limit is gauge invariant. So in the end, we come up with a somewhat roundabout indirect argument, and not in 2 dimensions. You can just do it brute force by some kind of explicit calculations.
Thank you. Thank you, Martin. Thank you for this excellent talk. I've been told by first, I should have the opportunity, at least myself, to tell you. And also I've been told by the organization to remind them, to remind the audience that there are other panels in the 6 other stage which are available on the platform, and they can choose one of them and jump there. Thank you for this good beginning of afternoon, and I hope see you soon in Lisbon in better conditions.
Yeah. Okay, thank you very much.
Thank you.